The latter part of 10.3 includes some tangency problems, which I must admit of relatively minor importance, particularly compared with section 4 of this notebook, arc length, important, and section 5 of this notebook, area, even more important. Nonetheless, let's talk about it. And probably the best way to handle tangency problem for polar curves is to convert everything into parametric curves and then simply use typical parametric curves. So step 1, plug in t equals to t naught, and traditionally the parameter for polar curves is theta, so theta equals to theta naught. That's basically what we do over there. Except of course you have to get a parametric curve first, so x is r cosine of theta. That's where you just plug in theta equal to theta 0, and y equal to r times sine of theta, and that's where you just plug in theta 0. And then if you get a slope, then you can get an answer through slope-intercept equation, and if the slope is undefined, then you can declare it as a vertical line x equal to x0. How do you find the slope? One way is to use this horrendous formula for polar curves, or another is to use the standard parametric curve. Which is better? Well, parametric curve method is far superior. It's easier to memorize, one less thing to memorize, and well, computation is not really bad either. If you somehow want to derive this, it's kind of like this. We want we want dy dx by chain rule dy d theta over dx d theta, and then calculate the derivative. Y is r sine of theta, so use product rule. Denominator is x, so r cosine of theta, so by product rule we get this kind of derivative, and the ratio is the derivative formula, the slope formula for polar curves. But that's not really useful. This one is much more useful, and I'd like to make a point with an example problem here. Let's select the second one. Well, here it is. Instead of going through the formula, let's just convert this polar curve into a parametric curve. X is r cosine of theta, and this is r. After simplification, what do you get? We get 4 cosine of theta plus 1. And that's not bad. It's pretty simple. How about y? Well, r times sine of theta. So after simplification, we got something like this. Sine theta plus tangent theta. So step 1, plug in theta equal to pi over 3. We have value. Plug in theta equal to pi over 3. We have y value. So we have point. Step 2, take the derivatives. Derivatives are pretty simple because polar curves became rather simple parametric curves. Step 3, find out the slope by the slope formula. Y prime of t naught over x prime of t naught. Plug in theta equal to pi over 3, do the computation, you get the slope. We know the slope, x0, y0, so we can answer the question by slope point equation like this, and as far as I'm concerned, this is the final answer and this is okay. For some reason, if you want to simplify it further toward a slope-intercept equation, here it is. You can break up the parentheses and rearrange and do something. By the way, here is the picture, visualization of the curve, and obviously this blue curve, the polar curve, has a vertical asymptote. And what is a vertical asymptote is something you can ask yourself. That's a little bit more challenging than finding out this equation of the tangent line, which is represented in red. Okay, that concludes the section 3 of this notebook, and then let's move on to section 4, arc length. Arc length formula goes kind of like this. Well, we want the same say ds computation as before. So dx d theta squared over dy d theta squared and square root of all that times d theta. This part is ds computation. The only thing that changed from parametric curve case was we have theta instead of t. But in this particular case, the latter formula is a little bit more useful because it's simpler. And consequently, the derivation of it is also important, so let's talk about it. So how do you derive this second formula from the first one? Well, we have to take the derivative, square it, and then take the derivative, square it, add them all up, and then take the square root and see how the simplification goes. Excuse me. X is r cosine of theta, y is r sine of theta. So by taking the derivative, you're going to get this expression, r prime cosine of theta minus r sine of theta, and r prime sine of theta plus r cosine of theta by product rule. Now, if I square them, well, this is what we are going to get. Complete square formula says a squared plus b squared minus 2ab. And this one is addition, so this is going to be a squared plus b squared plus 2ab. If you add them up, clearly you can see this minus 2ab and plus 2ab part will cancel out, and that will become 0. How about the other part? They become pretty simple too, because how about the second factor, r squared? That's common factor. You have sine squared plus cosine squared, which will add up to 1 by Pythagorean identity. How about the first term? This is common factor. We have cosine squared plus sine squared. Again, that's going to add up to 1. So what do you get? After simplification, we're going to get r squared plus r prime squared. So that's r prime squared, and that's r squared. So we change the order just a little bit, because that's rather traditional. And that's ds computation. So if you integrate that from theta equals to alpha to theta equals to beta, we're going to get the arc length formula for polar curves. By the way, it is traditional to use Greek letters for angles. Instead of t, we use theta. Instead of a and b, we use alpha and beta. Those are traditional. However, if you do not like those Greek characters, especially alpha and beta, you can use a and b just the same. Theta, on the other hand, I believe by now everybody got used to theta. Okay, let's talk about an example problem, and an example problem that I selected is cardioid. This is one of very rare, non-trivial polar curve that we can actually calculate precisely. So let's work on a cardioid. Before doing anything, let's see the picture. Let's see, is there a picture? Nope. Yes, there's a picture. That's what the cardioid looks like. We begin from 2, 0 in the right hand side, and then move counterclockwise all the way to the origin, and then go back to 2, 0. So clever students probably will calculate the arc length from 0 to pi, only the upper arc, and then simply double it. Actually, this is what I mean. Simply calculate the upper half and then double it. How do we do that? Well, here we go. Let's calculate the inside. We can convert everything to parametric curve and then go from there, but often that is complicated. Yes, you can do that, but sometimes that's complicated. So let's use this formula, r squared plus r prime squared. So r squared is just 1 plus cosine of theta squared. So by the complete square formula, you're going to get this. R prime squared is take the derivative, we get negative sine of theta, and square it, we have sine squared. If you add them up, what do you get? 1 plus 2 cosine of theta plus cosine squared plus sine squared if you add them all up, which is, well, right over here. Now, do you see further simplification? Do you see that cosine squared plus sine squared becomes 1? That's a key observation. And we have something like that. Now is the tricky part. As a matter of fact, if you remember what we did in cycloid part, you're not going to have too much trouble. But for others, if you did not study cycloid, then this could be quite troublesome step. As a matter of fact, it turns out 2 plus 2 cosine of theta can be written as 4 times cosine squared of theta over 2. As a matter of fact, this cosine squared of theta over 2 is 1 plus cosine of theta over 2. So by multiplying 4 to everything, you're going to get this identity. This square root is equal to that square root. The second square root is superior because this is square root of a square. This cosine squared and the square root outside will cancel each other out. Square root of 4 is 2, so we are going to get 2 cosine of half of theta, and we're going to need absolute value. Unlike that cycloid case, we're going to need that absolute value. Without the absolute value, and if you calculate the antiderivative, I think you're going to end up getting 0. And be careful about those kind of things. If you get 0 in the area problem or arc length problem, you must have done something wrong. But the mistake you made must be really trivial, which means even harder to find out. It's likely to a sign mistake. Did I tell you about calculating the arc length or only the top arc and doubling it by symmetry? That'll actually save you a lot of trouble. If you just calculate the entire arc, entire circumference, and if you do not be careful about absolute values, you may come up into trouble. So if you start off by reduced form, reduce arc length, and then double it, or if necessary quadruple it later, then you won't have much trouble. You'll have to do that anyway later on. This is what I did. Double and then just go from 0 to pi. And in interval 0 to pi, cosine of theta over 2 is positive. So we can get rid of this absolute value sign, and now we are free to apply the fundamental theorem of calculus. And well, here it is, a sine of theta over 2, and plug in pi, plug in 0, subtract one from the other, and we're gonna get yes, pi over 2, sine of pi over 2 is 1, so yes, 8 minus 0, we're gonna get 8, that's right. By the way, here is the justification through Mathematica, and I asked Mathematica to calculate r squared plus r prime squared total quantity square root, and then simplify, and this is inside the square root, and then that's what Mathematica spat out. And this doesn't really look like a lot of simplification, to tell the truth. Anyway, okay. And then the antiderivative is this one. Some strange reason we have tangent of t over 2 and something. That's because Mathematica follows a little bit different scheme than the way we do in paper and pencil method. And finally, if you take the definite integral from 0 to a to b, we get 4, and that's because a to b is 0 to pi. We have to double it, and the answer will be 8. Well, okay. Alright, there goes the justification and all. And in the next segment of the video, we're going to talk about the area problem. And I don't know whether I'll have time to talk about surface area problem. We'll talk about area first, and then if I have some time to burn, then I'm going to talk about surface area.